Hello everyone. Once again, welcome to this Cartesian e-learning channel. This is our fifth lecture of TYBSc Physics Paper First, Mathematical Methods in Physics. In this lecture, we are going to discuss length element, area element, and volume element in various coordinate system. Let us start. In previous lecture, we have studied general curvilinear coordinates u1, u2, u3. We have seen three coordinate surfaces, u1 constant surface along which u1 coordinate is constant, u2 constant surface along which u2 coordinate is constant, and u3 constant surface along which u3 coordinate is constant. As well as we have seen three coordinate curves, u1 curve, u2 curve, u3 curve. The curve intersecting u2 surface and u3 surface is u1 curve along which only u1 coordinate varies. The curve intersecting u1 and u3 is u2 curve along which only u2 coordinate varies, and the curve intersecting u1 and u2 surface is u3 curve along which only u3 coordinate varies. This way we have seen three coordinate curves u1, u2 and u3. These three coordinate surfaces and these three coordinate curves intersect at a single point. These three surfaces and these three curves intersect at a single point, and that point has coordinates u1, u2, u3 that we have seen in previous lecture. Then the tangent draw to this curve. We draw the tangent to this u1 curve, u2 curve and u3 curve. Then we get three coordinate axes. In this case, this e1, e2 and e3 are the three coordinate axes. Let us derive the length element, area element and volume element in general curvilinear coordinate system. For this, consider this point P having coordinates u1, u2, u3. And as we have seen, these three curves, u1 curve gives the variation of u1, u2 variation of only u2, and u3 curve is variation of u3. Then the tangent to u1 curve is the first axis, let it is a1 bar. Tangent to u2 curve is second axis, let it is a2 bar, and tangent to u3 curve is third axis, let it is a3 bar. Then this unit vectors e1 cap and e2 cap, e3 cap gives the direction of variation of u1, u2 and u3 at point P. Then consider a small volume. Let it is parallelepiped whose edges are dl1, dl2, dl3 extending along three direction e1, e2, e3. Then connect these two diagonal points by a vector dl bar. Let this vector is dl bar. Then let us see the three components of this dl bar along these three axes. This dl1 is component along a1 axis, which gives variation of coordinate u1, and direction is given by unit vector e1. Then the second component is dl2, which gives variation of u2, and its variation direction is given by this unit vector e2. And the third component is dl3, which is along third axis, which gives variation of u3, and this unit vector e3 gives direction of variation. Therefore, this dl bar, this vector dl bar is written like this. This three component. This is first component, which is gives variation of u1. The second component, which gives variation of u2, and this third component, which gives variation of u3. Then this magnitude that this length dl, this length element dl is equal to square root of this magnitude dl1 square magnitude dl2 square plus this magnitude dl3 square. This is the length element. This length element in terms of du1, du2, du3. This is because dl1 is equal to h1. In previous lecture we have seen dl1 is equal to h1 du1, dl2 is equal to h2 du2, and dl3 is h3 du3. Therefore dl is equal to square root of h1 du1 square plus h2 du2 square plus h3 du3 square. This is the length element in general curvilinear coordinate system, in orthogonal general curvilinear coordinate system. Let us see the area elements. The area elements are: the first area element TA1, TA1, this blue color area, this area having edges, this DL2, DL2 and DL3, DL2 and DL3, DL2 into DL3. DL2 is H2 DU2 and DL3 is H3 DE3. Therefore H2 H3 DU2 DE3. And this E1 cap is normal to this area. This E1 cap is normal to this area. Therefore this first area element. Then the second area element is along this A2 axis, is along this A2 axis having edges DL1, H1 DU1 and DL3, H2 DU3. Therefore DA2 is equal to H1, H2 DU1, DU3. And this E2 vector is normal to this area. Therefore DA2 is equal to H1, H3 DU1, DU2. Then the third area DA3, this top area DA3 having edges, this edge is DL1, this edge is DL2. For DL1 into DL2, and the normal vector is E3. This E3 cap, normal vector is E3. Therefore H1, H2, DU1, DU2, E3. This way these three area elements DA1, DU2, DA2 and DA3. Then the volume element. This volume element is product of these three edges DL1, DL2, DL3. So dV is equal to DL1, DL2, DL3. But DL1 is H1 DU1, DL2 is H2 DU2, and DL3 is H3 DA3. Therefore dV is equal to H1, H2, H3, DU1, DU2, DU3. This way, this is the volume element in general curvilinear coordinate system. This is the length element in general curvilinear coordinate system. This area element in general curvilinear coordinate system, and this is the volume element in general curvilinear coordinate system. Then let us see the length, area and volume element in Cartesian coordinates. For this, consider this point P having coordinate x, y, z. Then as we have seen, the three axes in Cartesian coordinate system, the three coordinate axes are x, y and z. And the unit vector along x-axis is I cap, unit vector along y-axis is j cap, unit vector along z-axis is k cap. Again, if we consider this volume element, that parallel pivot having edges dx, dy, dz, can connect these diagonal points by this vector dl. Again, this dl has three components. This dl has three components along x-axis, y-axis and z-axis. Along x-axis, the component dl1 is equal to dx and direction is I cap. Along y-axis, along this y-axis, the component is dl2 is equal to dy and the direction given by this unit vector j cap. And along z-axis, the component is dl3 which is equal to dz and the direction is given by k cap. Then the length vector, this dl bar is equal to this is the component of dl bar along x-axis, this is the component of dl bar along y-axis, and this is the component of dl bar along z-axis. Then its magnitude dl is equal to under root of square root of dx square plus dy square plus dz square. If we compare this is the length element in Cartesian coordinate system. If we compare this length element with the length element in general curvilinear coordinate system, then we get three scale factors. H1 is equal to 1, H2 is equal to 1, and H3 is equal to 1. Because all these three length element dl1, dl2, dl3 are length elements. Therefore, though there is no any multiplying factor, therefore h1 is equal to 1, h2 is equal to 1, and h3 is equal to 1. Then the area elements. The first area element dAz is along z-axis. This area element is perpendicular to z-axis. Area element perpendicular to z-axis dl1 into dl2. dl1 is dx, dl2 is dy. Therefore, dAz is equal to dy. If we write in vectorial form, then here we have to multiply it by k cap, because k cap is normal to this area. Then the second area dy along y-axis, that is perpendicular to y-axis. This area dy is equal to dl1. This edge is dl1, edge is dl3. Therefore, dl1 into dl3, that dx into dz, dx into dz. Vector form, here we have to multiply by j cap. Of j cap, this j unit vector is perpendicular to this area, normal to this area. Then the third area element is dx, is along x-axis, that perpendicular to x-axis, area perpendicular to x-axis, having edges this dl2 and this dl3, dy and dz. Therefore, dx is equal to dl2 into dl3 is equal to dy into dz. If we write in vector form, then here we have to multiply by I cap, this unit vector I, because unit vector I is normal to this area. These are the three area elements in Cartesian coordinate system. Then the volume element. Volume element dV is equal to dl1, dl2, dl3. dl1 is equal to dx, dl2 is equal to dy, and dl3 is equal to dz. Therefore, the volume element in Cartesian coordinate system dV is equal to dx, dy, dz. This way, this is the length element in Cartesian coordinate system. These are the area elements in Cartesian coordinate system. The volume element Cartesian coordinate system. Next topic, length element, area element, and volume element in spherical or polar coordinate system. In previous lectures, we have already studied these spherical or polar coordinates r, theta, phi. R is the distance of point P from origin, that is this length OP is r coordinate. The angle made by OP with z axis is theta coordinate. And if you draw the foot perpendicular from point P on xy plane, let it intersect at point R, then angle made by this line OR with x-axis is phi coordinate. This way we have seen these three coordinate r, theta, phi. As well as we have seen three curves, R curve. This R curve is along this R. This R curve is along the increasing direction of R. Theta curve is along the increasing direction of theta. Theta curve is along the increasing direction of theta. And phi curve is the circle, which is along this increasing direction of phi. These three curves we have already seen. If we move this point along R curve, then we get the displacement dr. And the unit vector along this R curve is er cap. If we move the point along theta curve, we move the point along theta curve by small angle d theta, then this distance, this displacement is r d theta into e theta cap, because the tangent to this curve is e theta cap. If we move the point along phi curve by small angle d phi, if we move this point along phi curve by small angle d phi, then this arc length is r sin theta d phi, because this distance of point from z axis is r sin theta. Because this angle is theta, this length is r, therefore this is r sin theta. r sin theta. This angle is d phi. Therefore, this arc length is r sin theta d phi. We multiply it by e phi cap because the unit vector along phi curve is e phi cap. We have already studied this unit vector along this phi curve is e phi cap, tangent to this phi curve, e phi. Therefore, r sin theta d phi into e phi cap is the change along phi curve. Then, if we draw this, move this point from P to Q by dl, then this dl bar, vector dl bar, if we change the position of point P from this position P to Q, then this dl bar vector has three components. One is along r curve, second is along theta curve, and the third is along phi curve. That dl bar is equal to dr into er cap. This is the displacement along r curve, r d theta into e theta cap. This is the displacement along phi curve. This is the component of dl bar along phi curve, and r sin theta d phi into e phi cap. This is the component along phi curve. This way, these three component along r curve, component along theta curve, and component along phi curve. And its magnitude, dl is equal to square root of magnitude of this component, dr square. Magnitude of this component is r theta, therefore r d theta square. Magnitude of this component is r sin theta d phi, sin theta d phi square. This is the length element in spherical polar coordinate system. If we compare it with the length element in general curvilinear coordinate system, this expression we have already derived for the general curvilinear coordinate. Comparing these two expressions, du1 is equal to dr, du1 is equal to dr, therefore h1 is equal to 1, h1 is equal to 1. du2 in spherical polar coordinate system, u2 is equal to theta, therefore du2 is equal to d theta, therefore h2 is equal to r. Comparing these two magnitudes, this h2 is equal to r. In this way, this second scale factor h theta is equal to r. du3 is equal to d phi because u3 is equal to phi. In spherical or polar coordinate system, u3 is equal to phi. Therefore, du3 is equal to d phi, and the coefficient h3 is equal to r sin theta. Therefore, this h phi is equal to h3 is equal to h phi is equal to r sin theta. This way, in spherical or polar coordinate system, the scale factors h1 is equal to 1 because this dr has length unit. This h theta is equal to r because theta has not length unit. Therefore, we have to multiply it by r. Then this r is a scale factor. In the same way, phi has not length unit. Therefore, we have to multiply it by r sin theta. This h phi, scale factor h phi is equal to r sin theta. Let us derive area and volume element in spherical or polar coordinate system. The area elements are the first area element ds bar. This ds bar is equal to dr into r d theta. Dr, this is dr, and this is r d theta. Therefore, this area PQRS, this area is the first area vector dr into r d theta e phi because phi is the unit vector normal to this area for r dr d theta. Then the second area is this dr, and this is r sin theta. Here also dr is r sin theta. For this area is the second area dr, this r sin theta dr d into e theta cap. Normal to this area is e theta cap. Normal to this area because this is theta curve. Tangent to this theta curve is e theta cap. Therefore, normal to this area is e theta cap. Then the third area is r d theta, this bottom area, r d theta, r sin theta d phi. This side is r d theta, and this side is r sin theta d phi. Therefore, this bottom area is the third area, r d theta, r sin theta d phi. Simplifying, we get r square sin theta d theta d phi into er cap, because normal to this area is er, this unit vector er. In this way, these are the three area elements in spherical or polar coordinate system. Then the volume element, dv is equal to dl1 into dl2 into dl3, but dl1 is dr, dl1 is dr, dl2 is r d theta, and dl3 is r sin theta d phi. Substituting, dv is equal to dl1 is dr, dl2 is r d theta, and dl3 is r sin theta d phi. Therefore, this volume element dv is equal to r square sin theta dr d phi. The volume element in spherical polar coordinate system. Let us derive the length, area, and volume element in cylindrical coordinate system. We have already studied these cylindrical coordinates rho, phi, and z. Rho is the distance of point P from z axis. Phi, if we draw foot perpendicular from point P on xy plane, then angle made by this line with z x-axis is phi coordinate, and distance of point P along z axis is z coordinate. Then if we move this point P along this rho curve, we already studied this, along rho curve, then the displacement is 0. If we move the point along phi curve, this red dotted line, this line, phi curve, by angle d phi, then this length is rho, this angle is d phi, therefore this arc length is rho d phi. And if we move this point along the z curve, increasing direction of z, then this displacement is dz. If we connect this diagonally opposite point P and Q, let this vector is dl bar. Then this vector dl bar has three components. One is along rho curve d rho, along phi curve is rho d phi, and along z curve is dz. Along rho curve, the unit vector is e rho cap. Tangent to this phi curve is a unit vector e phi cap, and along z curve, unit vector is ez cap. Therefore, dl bar is equal to this dl bar is equal to d rho into e rho cap. This is the magnitude of the change, and unit vector is e rho cap. Therefore, d rho into e rho cap. This is the component along rho curve. This is the component along phi curve, and this is the component along z curve. This d rho is rho d phi, and dz are the magnitudes e rho cap, e phi cap, and ez cap, unit vectors, which gives the direction of the change. Then the magnitude, this length element, is equal to square root of d rho square, this magnitude d rho d phi square, this magnitude rho d phi, and dz, this magnitude dz square. So this is the length element in cylindrical coordinate system. If we compare it with the length element in general curvilinear coordinate system, then u1 is equal to rho. Therefore, du1 is equal to d rho. Then comparing this, we get h1 is equal to 1, h1 is equal to 1, u2 is equal to phi. Therefore, comparing coefficient of du2 and d phi, h2 is equal to rho. This second scale factor, h phi is equal to rho, and u3 is equal to z. Therefore, du3 is equal to dz. Comparing this, we get h3 is equal to 1. This way, in cylindrical coordinate system, the three scale factors h rho is equal to 1, h phi is equal to rho, and hz is equal to 1. Because rho and z has dimension of length, therefore h rho is equal to 1, hz is equal to 1. But phi has not dimension of length. Or we have to convert it into length component, we have to multiply it by rho. Therefore, this h phi, scale phi, h phi is equal to rho. This way, these three scale factors, h1 is equal to 1, h phi is equal to rho, and hz is equal to 1. Then the area elements. The area elements are ds is equal to d rho dz. This is d rho, this is dz. Therefore, this front area is the area, and E phi cap is unit vector normal to this area. Normal to this E phi cap is the unit vector normal to this area. Then the second area is rho d phi. This rho d phi and this dz. Therefore, this area or this area, this dz rho d phi, this area is the second area, and E rho cap, because this is the increasing direction of rho. Therefore, unit vector normal to this area is E rho cap. Then the third area, ds bar is equal to d rho into rho d phi. This is d rho, and this is rho d phi. Therefore, this bottom area or this top area, top area. This is the third area, d rho, rho d phi. And normal to this area, the unit vector is Ez cap. Unit vector Ez cap. Therefore, ds bar is equal to rho d rho to d phi into Ez cap. This way, these three areas in cylindrical coordinate system. Then the volume element. The three length dl1 is equal to d rho, dl2 is equal to rho d phi, and dl3 is equal to dz. Then dv is equal to dl1 into dl2 into dl3, equal to h1 du1, h2 du2, h3 du3. h1 is equal to 1, h2 is equal to rho, h3 is equal to 1. du1 is equal to d rho, du2 is equal to d phi, and du3 is equal to dz. Therefore, in cylindrical coordinate system, h1 1, du1 d rho, h2 rho, du2 d phi, h3 1, du3 dz. Therefore, dv is equal to rho d rho d phi dz. This is the volume element in cylindrical coordinate system. In this way, in this lecture, we have studied the length, area, and volume element in general curvilinear coordinate system, in Cartesian coordinate system, in spherical polar coordinate system, and in cylindrical coordinate system. That's all this lecture. Thank you.